It's time for me to do a show, and Vladimir Putin decides it's time to invade Ukraine. I just want to do some dumb whiskey fueled nonsense and have a good time for a happy hour, but can I do that? No, can't do that. Well, you know what? I am going to do that. Take that, Vladimir Putin. I'm going to have myself a good time. Invading Ukraine, plunging the world into war. But we're not going to succumb to your pressures. I don't even know what the comrade. Yeah, we still call him comrade. That's fine. We're not going to succumb to your pressures, comrade. We're going to be talking about the size of the moon and the earth and the sun and the distances apart and how we can calculate that stuff, because that stuff is fun. It's actually surprisingly fun. It's surprisingly fun, and that's what's going to be. That's what's so fascinating about it. It's simple math, but it's actually quite fun. Surprisingly fun. It leaves me shocked every time I look at it. Like, how could it possibly? How could that be? But that's how the math works, and it's. Oh shit! This thing's on. Ladies and gentlemen, brothers and sisters, children of all ages, the sign says to drink, and that means it is time for us to begin the next installment of our show. Our show tonight, the Old Humble Whiskey Happy Hour. Cheers and salutations to all of y'all. Um, tonight's show, I'm the Old Humble Guy. This is our Wednesday night show. It's an hour-long happy hour. Kick back, relax, enjoy yourself. I'm having a drink. We are having our special reserve tonight. A little tickle in my throat. We went camping this weekend. Youth retreat for our church, a little youth retreat action. And it was a little cold. The cabin was a little bit drafty, and I was underneath a window. I was fairly well bundled up, but the window was still a little bit drafty, and I think I caught a little sinusy thing from the draft in the window. I'll survive. Don't worry about me. I'll be fine. It's just gonna be a couple days, and I'll be back to my beautiful, wonderful self. John Jacobs is in the house. Cheers, my man. Uh, won't help much. I'm what? Oh, modding a coin chain. I thought it said molding a coin chain. Like, what the heck does molding a coin chain mean? So here's what's up. Goodness, let me get this. Cheers to all y'all. Tonight's show. Tonight's show is going to have math content, but it's not going to be heavy math content. Don't worry. I've even got a whiteboard. It's not going to be heavy math content. I'm not going to like do formulas and stuff. I'm going to talk about it, and we're going to talk about it. This is actually quite fascinating stuff. Last week on Wednesday, last week's midweek happy hour whiskey happy hour show, I talked about the origins of the flat Earth theories and where they came from and where they started, and how it basically was a flawed experiment that proved. I forgot to take this thing off. Hold on. That proved, due to faulty logic, that the Earth was, in fact, pancake flat. But the reason it's the level experiment where the hypothesis is that if the Earth is round, then the water is also round because it conforms to the spherical nature of the Earth, right? And this dude sent a ship out, and it stayed level for far longer than he expected. So we concluded that the Earth is flat. It was a failed. It was an incorrect experiment because the Earth was, I guess, bigger than he expected, and he didn't take into account the refraction from the atmosphere and several other things. And I said that we know the Earth is round. The Greeks have known. We've known for over 2,000 years. The Greeks knew it was round. because they were then not only did they know the Earth was round, they knew the size of the Earth, and this is like basic middle school. I said third grade math, but it's really middle school math that confirm you can literally calculate using a hand calculator. Where's my hand calculator? Um, you can literally calculate using a hand calculator. I have one somewhere. Where's my hand calculator at? There it is. You can literally calculate the entire circumference of the Earth using one of these. It's not. It really is that simple. And that was the first calculation that the Greeks made as far as the size of celestial bodies. And having made that calculation, they were then able to compute the relative size of the moon, the distance of the moon, and then the distance of the sun, which was wrong, but it was the best distance that they had until like the 1600s when better, more precise calculations were made. And they were like, oh shit, the sun is a whole lot bigger than we thought. Um, and the reason why that math was wrong was because they were using very imprecise measurements. And when you have imprecise measurements that are off by just about a half a degree, and you extrapolate that over big spaces, then you get big errors. And that's just basically how it is. Um, and as I also said last week, this isn't a debate. I'm not debating whether or not the Earth is round or whether the Earth is flat because it's round. That's not a question. That's not a question. It's not a debatable topic. It's not something that should be kicked back and forth. Or maybe it is, maybe it no. 2 + 2 = 4. That's not a debatable topic. It is what it is. It is. It's a thing. Period. It is what it is. But the math that supports it and why do we know what we know is actually pretty fascinating. And I find it to be fascinating, at least. And this is the kind of stuff that you can actually talk about at a bar because you can make these drawings and do these computations literally on a napkin at a bar. It is not that complicated. It is actually quite simple. And intuitively, we know these things. It's just the numbers are so big, big, beefy numbers. They're a little bit mind boggling and they seem intimidating, but they're not really intimidating at all. They're really, 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 really simple. Um, but there you go. And you're seeing me on a Wednesday night, assuming you're seeing me on a Wednesday night. Cheers, Shark Homebrewing. Cheers to you. Assuming you're seeing me on a Wednesday night, you're seeing, well, I'm obviously, if you're seeing me now, you're seeing me on a Wednesday night. If you're seeing me in the replay, you're seeing me on some other night. But the reason we're doing a happy hour, a whiskey happy hour on Wednesday nights is because I started doing multiple whiskey happy hours all during the week. Our Thursdays are our big show, where we have the 2 hour show. I started doing a Tuesday and Wednesday show where we just talk about a topic. I bring in the chat. We talk about topic. Bacon's in the house. Shark Homebrewing's in the house, and John Jacobs is in the house. Cheers, everybody. Um, and you know, it's because I miss going to bars and I miss having these conversations and I miss talking to people at bars because I haven't done it in eons because I'm working late. I'm doing this stuff. I'm doing stuff late. I don't get a lot of outside time. They don't let me go hang out with the people like they used to. But this really is the type of stuff. Uh, we can look at people and say, at the bar, like we know the Earth is round, and here's how we know it's round. I can show you, like literally. For example, here's the whiteboard. We know based on shadows at the equator. This is what's cool. If you have a pole, imagine that as a pole sticking vertically up out of the ground, right? That's a pole sticking up vertically like this. It's a pole sticking up out of the ground. When the sun approaches it from this side, the sun's coming from this side, its shadow is like this, and then it's a little bit shorter, and then it's a little bit shorter, and then it's a little bit shorter, and then it's a dot. And then as the sun progresses this way, it's a little bit longer, a little bit longer, a little bit longer, a little bit longer, a little bit longer. Now, if the Earth was a flat circle like this, and the sun was going around like this, that shadow would go like this, and a little bit shorter, and a little bit shorter, and a little bit shorter, and then it would extend out that way at the equator, no matter where it was at the equator, because of the direction the sun was. So we know that the Earth is like this, round, and that the sun goes that way and then comes back around that way. We know this based on basic geometry and basic facts about how things are, basic observations. We don't have to go to space and see it happen. We know this. So that's the basic baseline understanding. And we also know this because when we have shadows here and shadows here, and the sun's over. Can you see that? You can't fucking see anything on this whiteboard, can you? Anyway, the sun's rays go like this. This casts a shadow like this, and this casts a shadow like that, and you don't see that shadow. You don't see that shadow at all on the equator, but you do see that shadow up there. And it just so happens that there's this dude in ancient Greece who noticed that, and he's like, "Oh, neat." So the sun goes down into this well in this city called of Syene. I think it was Syene. And on the solstice, the sun goes all the way down into the well. But on the same day in Alexandria, about I don't know, I think it was 5,000, not 5,000 miles, 5,000 meters, 5 kilometers, something like that. I don't know. Somewhere up in the north, the sun never goes like straight down to the well because it casts a shadow on the solstice like that. Like this. It casts a shadow like that because it's further north. And so they measured the angle of that shadow on that triangle that it made. True fucking story. Kid you not. I measured the angle of that triangle, and it turns out that angle up here was something like 7 degrees. And he determined, he hypothesized that if that is a 7-degree angle, then this, knowing how triangles work and how circles work and how spheres work, that circle right there, that triangle, or that was 7 degrees of the surface of the Earth. And he knew that based on the size, if you knew the distance between 2 points and the angle between those 2 points on the surface of a sphere, then you could calculate the entire circumference of that sphere. This is in like 300 BC. He calculated the circumference of the sphere, and it came out to be, let me check my notes real quick, make sure I get the right number, something to the order of 24, I think he calculated with like 26,000, which was slightly larger. 40,000 kilometers is the size, is the circumference of the Earth. The dude's name was Eratosthenes. Eratosthenes was his name, and that's like in 300 something BC, 200 something BC. Pythagoras hypothesized that the Earth was round. Aristotle proved it, and Erasmus calculated the size, the circumference of the globe. And this is like 100 years before the discovery of pi. The ratio between the circumference and the diameter of a sphere. And he was only off by like 2% of this actual size of the globe. So, and you can do this calculation. It turns out the actual angle, they measured it to be about 7 degrees. The actual angle at that height was closer to 8 degrees and this is how we know what the actual angle would have been, because we know the actual circumference of the globe today. So we can use that same math and go backwards and say, look, we know the circumference of the globe. We know the distance between the two cities. So we also know what the angle of the actual shadow was. And again, it has to do with precision. It has to do with altitude. It has to do with all kinds of other things. It could be the variance. A 2% variance is like practically nothing when you're talking about 40,000 kilometers, which is like 25,000. I think 25,901 miles. I think. Don't hold me to that. You can Google that. You can see what it is. But you can do the math. It's actually It's actually simple math because it's uh, 7 degrees of 360 equals like whatever it was, 900 over x. That's the math. Can you see that? Yeah, you can see that. And then you do the math. Uh, 360 times 900 equals 7x. Divide by 7. There you go. That's how you do the math. And I don't need to calculate it. I know how big the Earth is. That's the point. So you see, that's how we knew, and that was the hand wave that I did last week. We know we know the math. We've done it. We've done the math. We've done it. We know how it is. We know the size of the Earth. But we have known the size of the Earth, and that was like the vertical circumference of the globe from pole to pole around. And again, this is 100 years before pi was discovered and determined. Um, I see chat move. I go over there and look. So this is like 100 years before pi was determined. I think because pi was discovered in, I believe, 200 BC, and this is like 300 BC when they're making these calculations and making these determinations. The Greeks were cool dudes. They apparently had a whole lot of time on their hands, a whole lot of time on their hands, because they basically sat there and thought about this stuff. And they're of course sitting there with their in their philosophical whatevers and chilling out, and they're like, well, how big's the moon then? I mean, if the Earth is this big, well, how big's the moon? And of course, I did this hand wave. Like, we know how to do the math. We've done this before, but I didn't touch on the actual math. When I was talking about the origins of the flat Earth theories last week, I just we know how to do this stuff. But I didn't actually mention how we do this stuff. And how we do this stuff is pretty cool. At least in my opinion, I think it's pretty cool. In my opinion, is the one that works. And what prompted this was I got a comment from somebody saying that the Earth is much bigger than we've been told. Well, no, actually, it's not much bigger than what we've been told. We know how big the world is because we can measure how big the world is. We can measure it. I mean, you can literally call up somebody in Dallas, Texas, have them take a meter stick and stick it on the ground and measure the length of the shadow from the meter stick, and do the same thing in Houston. That's 400 and what's the distance between Houston and Dallas? 250 miles, something like that. you can, as long as it's a precise measurement. Don't get me wrong; it has to be a precise measurement. You know the day and the time, and you get the length of that shadow, and you get the length of your shadow, and you can determine the difference between the length of the shadow cast in Houston, the length of the shadow cast in Dallas, 250 miles away, and then from those two data points, you can extrapolate the entire circumference of the globe, because you know the distance between the 2 points, you know the difference in the two angles that are being created. So you can determine that angle, and you can say, okay, this is whatever 63 degrees, that one's 64 degrees. So you have 2 degrees of separation, or 1 degree of separation. 63, 64. You have 1 degree of separation. 1 degree of separation is X number of miles. X number of miles times 360. Boom! You have the size of the entire fucking globe. It's easy, easy, easy math. You can do this. Anybody can do this. Children in middle school, elementary school can do this. You measure a 1 foot okay. So that was the first cool discovery back in the 300s BC. When they were like, this is the size of the, and we know this because it was written down. We saw it. We can replicate these calculations. And they were off by a little bit because of the imprecise nature of the measurements that they were taking. I mean, it's not like they were using laser measurements and stuff like that. But here's the next cool thing that they knew about triangles and stuff like that. Let me wipe off my whiteboard here. I can't believe I'm using a whiteboard. I'm not even a professor. one cool thing that they knew about triangles is if you had a triangle that was like so, that's a terrible triangle. And then you had another triangle that was like, God, that's terrible too. Another triangle that was like so. And if these angles were the same, if those angles were the same, and you knew that the this leg was 2 times the length of this leg, and this leg was 2 times the length of this leg, then you could determine what this was. These legs are also proportional to these legs, as long as this angle was the same. That's important to know. Because if you hold up your thumb to a building and you block out that building, then you can measure the distance between your eye and your thumb. And if you know the size of the building, you can measure, you know how far away that building is. You know that the building at least has to be proportional to this distance from your eye to your thumb, and you know the size of your thumb to the building is proportional. That, like, if you block out that building, you see what I'm saying? If you block out that building from your eye to your thumb, then the distance between your eye to the thumb is the same proportion as the size of your thumb to the building. So if this is 1 to 180, then the proportion in size from the building to your thumb is also 1 to 180. So you can take your thumb, multiply by 180, that's the size of the building. This is very important to know because we all know that you can take your thumb, you can take a small coin, you take a small disc and hold it up in front of the moon. And if you hold the disc up in front of the moon, you know, proportionally speaking, the size, because you know the distance between your eye and the disc, and you know the size of the disc and the angles and all that other stuff. Because you know all of these little pieces of information, you can then extrapolate out from your eye to the edges of the moon how big the moon is. You can determine the diameter of the moon by holding a disc out from your eye. Or at the very least, you can determine the relative size of that moon by holding it out, because you know the size, the size of your eye to the size of the disc, and then the size of the disc that covers up the entirety of the moon all the way out. You know instantaneously that the moon is very large, and very far away. And you may not be able to determine the exact size right away, but that is exactly how, that is exactly the methodology that they used to determine the relative size of the moon and the specific calculation. Let me see if I can find it in my little notebook here. Yeah, that's exactly what they did. They so that was the second big discovery, was the size, the actual size of the diameter of the moon. And again, the way they determined that was these Greek dudes were very clever, because basically, let's see if I can show it to you. If you're a person, and you have a little disc here, and you know the size of the disc. There's another disc somewhere off over here, and you can. Well, that's terrible. That's absolutely terrible. Make sure that's a straight line so that it looks better. And then there's this straight line here so that it looks better. You know that this and this are proportional to this and this. You know this. You know this to be true. Hold this. That's how angles and sizes and stuff like that work. That's how they know the size of the moon. The width of the moon. That's how the Greeks knew the width of. We know the width of the moon because we have laser measurements and all kinds of other nonsense. We can send a a laser to the moon and back and determine by the time it takes for the laser to bounce off the moon and come back to us, the distance that the moon is from us. The Greeks could take a little disc and hold it up to the moon. You could take a little disc and hold it up to the moon and then determine just by ratios of the distance of the disc from to your eye and the width of the disc and the distance to your eye versus the width of the moon and the distance, and you know that that those proportions are the same. That's how they do it. That's how it was done. You know the proportions are the same. But it gets even better. And this one's a little bit more complicated. So I'm going to take a quick drink to unfurl the complicated nature of this one. Okay. So they know, based on their math, or rather, let's say they assume. They assume, based on the math, that works. So they feel fairly confident. They make these assumptions that the Earth is this big around, the moon is a relative, proportionality out there that's somewhere out there still. They don't know the exact distance that the moon is from the Earth yet. They have a pretty good idea of it, though. They can make this calculation with the proportions of the size and the distance and the length of that triangle leg and all that stuff. You figure it out. They've made their calculations. They understand. They have an idea. And now they're trying to figure out the actual size of the moon. So how do you do this? So what they do is they make a couple of logical assumptions from observing the solar eclipse and observing a lunar eclipse. So when they first observe the solar eclipse, the moon passes in front of the disk of the sun, right? So it passes in front of the disk of the sun, and it leaves a little circular shadow on the face of the Earth. Little circular shadow on the face of the Earth. And they make the very correct assumption. It's not all over the Earth. So the moon is definitely smaller than the Earth because it leaves a shadow that's smaller than the whole Earth because the shadow doesn't cover all of the Earth. It only covers a portion of the Earth. And they can deduce that the moon is smaller than the Earth because when there's a lunar eclipse, the other way around, when the moon's over here and the Earth is here in between the sun and the moon, the Earth's shadow covers up the whole moon. The whole moon gets plunged into a lunar eclipse as it passes through the Earth's shadow. So obviously the moon is the same size on both this side of the Earth and that side of the Earth. But the Earth's shadow is larger than the moon's shadow at the same distance between the two. So they know that the moon is smaller than the Earth. How much smaller? They don't know the answer to that question yet. This is where it gets really interesting or really exciting. What they end up doing is they observe the amount of time it takes for the Earth's shadow to go across the moon. At the distance where the moon is from the Earth, they observe the amount of time it takes for the Earth's shadow and the amount of the size of the shadows. And they determine from this as, because there's the sun over here and light comes out in parallel lines, right? Like so. The Earth is here and it casts a shadow that's like this. And somewhere in here is the moon, and they figure out as the moon crosses through the shadow this way. Y'all see that? Y'all see that? There it is, white balance. Thank you very much. They figure out that there's the moon there, there's another one and a half. It's a terrible drawing. They figure out that the moon is 3.5 times the size of the Earth, based on the amount of time it takes for the Earth's shadow to cross over the moon. So the Earth is 3.5 times the size of the moon. They do the math. And the moon, the diameter of the moon, turns out, I wrote it down so I wouldn't forget the number. The moon is about, what is it, about 1,000 miles? Is that the number I'm thinking of? I didn't write it down. I'll be damned. Well, the Earth is about 8,000, 7,900 miles across. 7,900, I think it's about a little bit more than 1,200 miles. 7,900 divided by 3.5. Oops, 7,900 divided by 3.5. I did not. So the moon's about 2,200 miles across, I guess. I don't remember. I didn't write it down. So I don't remember the exact numbers. But that doesn't matter because we know that it is farther away than 3,100 miles. And we also know diameter of moon. 2,159 miles. I had 2,257 on my calculator. So again, not exactly precise because they didn't have like atomic clocks and all that stuff. And also the distances between the distance between the Earth and the Sun, the Earth and the Moon, they're not. It's not perfectly round orbits. They're kind of ovarian, oval, oblong. That's the word I'm looking for. Elliptical. That's the word. Elliptical orbits. So we know the distance is about, what is it, 900 and something miles? 905,000 miles, based on the 108, the ratio of the size of the disk, the distance from your eye, and the disk way out there. We know that. We know the ratios and all that. How far away the moon is. We know how big the moon is. We know how big the Earth is, right? Here's the thing. All of these computations work together to confirm what it is that we think we know, and conform with observations of reality that we see in the world, right? Like we can look out there and see the moon takes up about a half a degree of the sky. You know, the sky is 360 degrees around. You know, you slice up a degree. The moon's about 1 degree. We know this. We know how triangles work. We know how math works. We know how sizes and shapes and all that stuff. For the moon to be the size that it is in the sky and be 3,100 miles away, like the current flat Earth hypothesis says, that means the moon would have to be about 27 miles across. That's why I said this isn't a debate. We know certain things to be true. We hold these truths to be self-evident. But not only are they self-evident, we can compute them and calculate them and confirm them. If you make a triangle, you draw the triangle out, and the top degree is 1/2 of a degree. That means it's an isosceles triangle. Isosceles triangles being erase. Isosceles, yeah, I do have the light on. Isosceles triangle where you have one big long triangle like that, and this is 1 degree. So that would be your eye down here. This is the moon. That's the moon. You see that? That's the moon. I wrote moon above it so you know. For this to be 3,100 feet or 3,100 miles, we know we know that this has to be 27 miles. We know this because this can be calculated. We know the bottom. We know the degree, the angles of the degrees, and all that. And if the moon is 3.5 times the size, or the Earth is 3.5 times the size of the moon, because of the amount of time it takes for the Earth's shadow to cross over the moon, then that means the Earth is like 95 miles across. 3.5 times 27 is something like 95 miles, which means the Earth is no bigger than the distance between Houston and Galveston. That's not right. That's not even close to that. Can't. That's impossible. The math doesn't work. Is what I'm saying. Um, does anyone believe the moon is made of cheese? No. Nobody believes the moon is made of cheese. Although I do remember that from the Bugs Bunny commercials, or Bugs Bunny cartoons, where they would go to the moon and it would be made of cheese, and that was a that is a fond memory of my youth, of the moon being made of cheese. And I believe there was a Wallace and Gromit episode where they went to the moon to get cheese as well. But see, what I'm saying though is this is how we know reality. Nobody's lying to us. NASA didn't exist in in BC 300 to create a globe that is 25,000 miles around. NASA didn't exist when they were determining the size of the sun. I guarantee you, when Eratosthenes first computed the distance of Earth to the sun, it blew his fucking mind because the sun was so much bigger than he thought it would have been. And it's even bigger than he thought because he had a wrong computation the first time, a very wrong computation the first time. And this is how they did that. This is actually quite clever. Let me show you. They took the moon. All right, let me show you this. They had the moon, and it was in the middle of one of its phases. So this side was dark, this side was light, which means the sun was over here. And he figured if the sun was here, giving its light this direction, right? Then this would have been a 90-degree angle, making a triangle with Earth, which was down here somewhere. Very clever idea, because if you know it's a right triangle, you can compute all kinds of stuff. And this is very poorly to scale because it's really more like, it was really more like this, but this is the Earth and this is the angle. And he claimed that this was like a 3 degrees, which meant this was, if that was 3 degrees, then this was 90, then this was 90, this was 90 minus 3. Yeah, so this was 87 degrees. And then he computed the distances based on that, and he was off, wildly off, because that is way less than 3 degrees. It's more like 0.3 degrees. And it's actually even smaller. It's like 0.15 degrees when it's full moon. But it was a stellar effort on his part, and that computation held up for like 1900 years until the 1600s, when Copernicus fixed it. But very intuitive, very clever. These guys would sit around and they would drink wine in their little philosophy tents or whatever they would do. Their agoras. I think that's what the Greeks called them. Their academies. And they would sit there and they would drink their wine and they would theorize about triangles and stuff. And like the basic geometry of the universe. I don't even want to say the universe. The basic geometry, like we know, for example, the sun is here. We know that Mercury and Venus and Earth we know that Mercury and Venus are on the inside because they disappear behind the sun, and we only ever see Mercury and Venus over here and over here, and then they disappear because they go around and they disappear behind the sun. We can't see them when they're in front of the sun. We can't see them because they're in front of the sun. We can't. But fun fact, they figured out the size of the sun. They finally were able to compute the actual size of the sun based on, turn it this way. So you had the big old sun, like so, and Venus would transit across the sun, and they could track the transit of Venus across the sun, and they could watch it. They could measure where on the sun this transit happened vertically, right? So what would happen is a little old Earth over here, with different points on Earth, Venus would be here. They'd watch it, and it would transit the sun right here from that latitude. And at this latitude, it would transit the sun here. And from this latitude, it looked like it was transiting the sun here. And from this latitude, it looked like it was transiting the sun here. And they knew the angle between here and here was this. It was the same on this side. And then that means that the distance from here to here was X number of degrees, and they could extrapolate that out based on the distance to the sun. Holy shit. Are you kidding me? No, I'm not kidding you. That's exactly how they determined the size of the sun. Boy, I'm telling you, they knew the distance from Earth to the sun based on the same type of triangulation measurements that they did with the moon. They did the same thing for Venus. They figured out the distance from Earth to Venus and Venus to the sun, and then they used these, it's called parallax measurements, where you're on one latitude on Earth and you're basically looking down. And you do this when you're hunting. If you go out hunting, you hold if you line your gun sight up and you close one eye, you're looking straight down the gun barrel. You close the other eye, you're looking across the gun barrel. The gun barrel is going this way. This eye is lined up over here. And if you're a left eye dominant individual like me, that can throw your aim off ridiculously. You have to actually physically close your left eye in order to, can't see, you have to close your left eye in order to line up your right eye with your gun sight so that your gun is shooting straight. If you don't close your right eye, your left eye lines up the eyesight on your muzzle, your barrel, and your barrel is going this way, and you're looking this way, and you can't shoot a goddamn thing because you're shooting all over the horizon because you're lined up wrong. That's the same principle they use to figure out how big the sun is. They go to London, and then they go to Sao Paulo in Brazil, and there's a big enough distance between London and Sao Paulo, and they watch the transit of Venus, and they see Venus on one part of the sun, and from the other latitude, Venus on the other part of the sun, and they can calculate those angles because they know the angle based on where they're at on Earth. And you can't do that if the Earth is flat. That's why this isn't a debatable topic. It's just, it is. It is what it is. It is what it is, just like 2 + 2 = 4. And that's what's so absolutely, I hand waved, like this is big brain, high level thought type of stuff, but it's very basic math. It's very basic geometry. This is geometry that they teach you in middle school. With like the angle of incidence equals the angle of reflection. This is how they teach you to play pool. This is how they teach you to do marbles. This is how they teach you to play bocce ball. This is how they teach you to do all these things. The angle of incidence equals the angle of reflection. So you go in at 45 degrees, you leave at 45 degrees. This is what they teach you. And this is the same basic math, the same basic geometry that they use to figure out how big the sun is. They figure out how big the moon is, the distance between the moon and the Earth. They figure all that you can't exactly take a piece of string from the surface of the Earth to the surface of the moon. You can now because there's reflectors on the moon, because we landed people on the moon. We actually went there and landed people on using calculations based on the fact that the Earth is round. We landed people on the moon, put giant reflectors on there. You can literally take a string from Earth, it's a laser string, and shoot it at the moon and bring it back and find out the distance from the Earth to the moon. And it was really, really, really close to the distance that the Greeks thought it might be. They were right. They were very close to right. But because they were measuring time with sundials and hourglasses, they weren't exactly precise. Thank you there, Bourbon Bounty. Cheers to you. Thanks for showing up in chat. We got chat all up and down. This is reminds me that there's still a shot of solid snake lining up sniper. Yeah, I mean that we know it, like intuitively we know these things to be true, and that's it. The parallax computations is the same way that we do with stars way out there in the cosmos, but we do it with a little bit bigger scale because we'll like take the measurement in June and then take the measurement again in December. So we're on opposite sides of the sun. So there's like uh, this giant angle that we're working on here because the distances are so vast in space. The distances are vast in our solar system, but Earth's also very big, so that helps. And we can take those measurements, and it's really cool. And again, if the moon was only 3,100 miles away from the Earth, it would only be 27 miles across. We know this because of math. We know this because of math. The size of it in the sky is indisputable. You cannot change the size of it in the sky. You cannot change the width of it in the sky. It is what it is. The actual time it takes for the Earth's shadow to transit it doesn't change during a lunar eclipse. We know what that is, which means the Earth's shadow comes down to a point, and somewhere in there is the moon. We know this. We know the distance where the shadow comes to a point. We know the distance because we know the width of the Earth. We know all these. We know all of these things to be true, because if they weren't true, then the math wouldn't work. You can't, A plus B equals C, and if A plus D equals C, then B equals C. We know this to be true. Like this is how things work. This is how the world works. Uh, so anyway, I was just scanning over on chat one more time. But we know these things to be true, and if you build a triangle like that, an isosceles triangle, the distance between, and then knowing the size of the Earth and knowing the relative size of the Earth to the moon, we know that the Earth could only be 95 miles across. Like, but we also know that the Earth is not 95 miles across. We know that the circumference of the Earth is 25,000 something miles. And now that we understand the relative relationship between circumference and diameter, known as pi, 2 pi r is circumference, which means circumference divided by pi is 2r, which is d. And we all like the d. I know y'all do. Some people do. Everybody likes the d. Big diameter of the Earth. We know this. And we also know that the diameter of the Earth is about, 7,900 miles? Something like that? Yeah, the diameter of the Earth is something like 7,900 miles. We also know that if you shrink the Earth down to the size of a cue ball, it would be smoother than the cue ball. That's a fun fact. That's how little relief there is from highest point to lowest point based on the entire size of the Earth. That's a whole nother thing. If things weren't curved, pi would not exist. Oh, of course, that's exactly true. Because we all know that pi are round, even though pi r squared is the formula. Pi are round. That's why. That's why pi exists. Natural log. I don't know what. That's outside of my understanding. But I know what logarithmic functions are. So I know what you're talking about. Anyway, but that's how we know these things. That's why it's not a debatable point. That's why last week's show was just basic origins of the theory, not is it? No, it's not. That it's not a debatable point. We know the size of the Earth. We know the size of the moon. We know the size of the sun. We know the distances of these objects, and we can prove it with middle school math. Middle school. We're talking 7th grade math. This is not at all complicated, which is why I say in the intro panel, guys, it's really simple. It really is simple. It's really simple. It's not drastically complex. You could literally call up your brother in Wisconsin or wherever, and as long as you know the lateral distance between the two cities, between Wisconsin and Mexico City or Houston and Dallas, as long as you know the lateral distance north south, you can compute the distance, but the circumference of the Earth. You can do this with a calculator. You could do it with a pen and paper. It's not that hard. It might be a little bit hard to get a very precise measurement if the cities are particularly close together. But man, I'm telling you, it's not hard. It is really, really, really simple. And we also know, for what it's worth, I mean, the Greeks didn't know this because they didn't know that Australia existed. They didn't know that there was a south of the equator. They didn't know about Africa and places like below the equator. They just kind of knew like Egypt and a little bit south. They didn't know much further than that. We also know that the moon is upside down in Australia and that they see different constellations in the southern hemisphere. They don't know who the fuck Orion is. And they don't care. They can't see that they can't see the Big Dipper. They can't see the Little Dipper. They don't know who Draco is. They don't know who Hercules. They don't know who these people are. They don't care. They can't see those constellations. They don't care. It's a whole different sky in the southern hemisphere. And the moon's upside down. And they have kangaroos. The southern hemisphere is completely different. Gorgeous women, thong bikinis. Beach volleyball and amazing. Anyway, I'm getting sidetracked. The southern hemisphere is an amazing place. It's vastly different from what we have up here. But because it exists, because the southern hemisphere exists, we know the Earth is round. This is the math. We know this shit. It's not a debatable point. It's not an arguable topic. But these are this is what I find to be just absolutely fascinating about this. There's scores of YouTube videos about this. All you got to do is put how did the Greeks figure out, or how did the Greeks determine the size of the moon, or how did the Greeks determine the Earth was round? How did the Greeks measure the circumference of the Earth? Whatever, how do you use shadows to measure the circumference of the Earth? Scores of videos, absolutely scores of videos. I might put a couple of the links in the description of the videos that I watched to reinforce and remind me of how we did this. But it's the same way. You can hold up a little disc. Use my cork here. You can hold up this disc and blot out the sun. You can use that same measurement, or blot out the moon if you're so inclined. You can use that same measurement, because that's a triangle from here to the point. From here to the point, you know the distance from your eye to the cork? That's the measurement of the the triangle. This would be the same proportion if you extrapolated it out all the way to wherever the moon is. That same angle, all the way out, that's how you know how big the moon is. That's how you know the size, or at least the distance. You know the distance, you know the size, you figure all this shit out. Based on based on the way that it transits. It is absolutely fascinating. I encourage people to go check this stuff out because math is surprisingly interesting and fun. I find it to be just deeply fascinating, and I can do math all damn day long. That's basically what I do in my job. I'm calculating proof gallons and determining how many gallons of water I have to add to alcohol to make it 90 proof and not 110. Uh, that's my job. But I also find this stuff to be it's kind of a stupid hobby, but it's a it's fun. It, not many people do math problems in their spare time. And maybe one of these days I'll do the problem. Like if you have the circumference problem, you have two circles like this. You have two circles. One is rotating around the other. How many times does the one on the outside go around as it circles around the outside? The answer is always the ratio of the outer to the inner plus 1. And there's a reason for that. If it was a square, for example, if we have this circle going around the outside of a square, it starts here, goes all the way down, then it goes around the corner, goes all the way down around the corner. It's a little bit more visible on a square because you have the outer angles. It's like a whole extra. Anyway, maybe I'll do a whole show about that because it's like a paradox. If you have two coins and you rotate one around the other, the one on the outside goes a whole extra rotation. But if it was on the inside, it would be like half. We'll talk about that some other time. But we're coming to the end of our happy hour. Ladies and gentlemen, brothers and sisters, children of all ages, let me take a quick look at chat real quick. We have a math major in the house. What? Who's the math major? Bourbon Bounty's the math major. Hey, Twisted. Cheers. Um, let's scan back up here. If things weren't curved, it wouldn't have pie. Yep. I'm wrapping up my current BS work. Be a little slow down before July. Oh. Twisted Art ladies in the house. Cheers. Bacon. I did not know you were a math major, Bourbon Bounty. There's not a whole lot for math majors to do in the world unless you're into statistics or you go into the statistical world or actuary or math majoring. That's a tough major too. Theoretical numbers, I assume statistical things, stuff like that. Um, I was a business major. I was no specific talents. That was my major. Um, let's see what we got. Math major. Pecan Pie should have learned how to make it from my. Oh yeah, there's a whole lot I wish I had learned from my grandmother. Um, I've got some stories, but one of my favorite recipes from my grandmother is she taught my uncle Clyde the joy of peanut butter, and sugar. And he would sneak me a bowl of peanut butter, and sugar. Not like a whole like heaping bowl like of ice cream, but like you know 3 or 4 spoonfuls of peanut butter, and sugar. It's literally that. It's like 3 or 4 spoonfuls of butter, 3 or 4 spoonfuls of peanut butter, and then a couple of generous helpings of sugar. Mix it together. It's like the inside of a Reese's peanut butter cup. It is so good. But when I was at my grandma's house and my uncle Clyde was there, he would sneak it to me in the kitchen, and I would go scamper off into the canning room and eat my special treat. And it was one of my fondest memories of that house. It was very cool. Also, laying on it was an old farmhouse and had a ventilation grate in the hallway. So it had one of those main hallways that went down the middle of the house, and at the end of it, there was a ventilation grate to have circulation through the attic. And you could lay on that grate and listen to the adults talk in the kitchen, and we used to do that too. Good times, absolute good times. Of course, the upstairs, we always said the upstairs was haunted because that's where one of my uncles died. But uh, as a grown up, I don't, not as a grown up, I don't believe in ghosts anymore. I don't buy into that. So um, it was just a cool old house, and it had a murder room above the garage. Uh, and we know the kangaroos. Uh, we know the kangaroos why the toilets flush backwards. Uh, More of a statistics guy. Yeah, okay, I got you. Computer security and risk assessment. See, I was not a statistics guy until I got my MBA. My MBA gave me a deep, deep appreciation for statistics because I finally learned how they worked. Uh, the difference between the probability of something happening at any given time and the probability of something happening for this particular airplane. Uh, that was, you know, the chances of these numbers being drawn in the lottery versus the chances of any numbers being drawn in the lottery. Um, Man, I sat there for night after night after night learning Bayes' theorem backwards and forwards and forwards and backwards and upside down and left and right. And I can disassemble Bayes' theorem. Let me explain what Bayes' theorem is for the non-math geeks out there. Um, you've got Bayes' theorem is basically giving you, I'm going to describe this really badly, Bourbon Bounty. Don't be mad at me. Basically giving you the probability of something happening given that something else has already happened. Something else related to that has already happened. So, like, a great example is given you've gotten a positive test result, what's the probability that that test result was a false positive or a false negative, or a false positive or a true positive? So if you picture the outcomes in a kind of a grid, you can have you have a negative outcome that's actually positive. You can have a positive outcome that's actually positive. You can have a negative outcome that's actually negative, or a positive outcome that's actually negative. So you have the four probabilities. And given that this condition has already been uh, fulfilled, some proportion of positive test results are going to be false positives. Some proportion of positive test results are going to be true positives. So, given that you've already gotten the one result, what's the odds that the second outcome is coming? It's kind of a conditional variable after the fact. That was like the entire thrust of that entire class, and it drove me absolutely bonkers trying to figure out how to do the math until I finally sat down and the problem we kept working on is you have a bin of bananas. There's Dole bananas and Chiquita bananas, and a portion of the Dole bananas are rotten, and a portion of the Chiquita bananas are rotten. Given you pulled a banana out and it was rotten, what are the odds that it was a Chiquita? That was like the question, or I think that was the question, and it kept boggling my mind. And it finally figured out the solution to the problem when it finally cracked open for me was when I was looking at it going, there's only 7 rotten Chiquita bananas. So like, and that's when it all like the scales fell from my eyes and I understood the problem all of a sudden. Like there's only 7 of them, so the odds have to be 1 in 7, right? And like I worked out the math or whatever it was, 7 out of 11 or something like that. Uh, oh, we got a troll in the house. Do I have any mods to take care of that goober? Do we have? I thought Russia was busy invading Ukraine. How are they? How are they available to send trolls out our way, huh? Anyway, thanks, Vladimir, comrade. Can I do it on this? There, I got him. There you go. Yeah, statistics work over time. Uh, can I remove him? I can. but I don't want to just remove him. I want to put the user in time. What do I want to do? I want to hide him on the channel. There we go. And then, okay, cool. Will it still show it? Ah, it shows that it's been hidden by Old Humble Distilling Company. Good deal. Ha! Take that, Vladimir's pet. You see, I want to do a show tonight, and Vladimir has to go and invade a whole country. And then we get his damn trolls coming and bugging me. What a dot Indian. I believe you. I trust you. Uh, but hey, it's time to wrap up the show. We've had our fun. I would love to keep going, but I've got this. I'm nursing this little cold that I got going on right here. I really need to get some sleep and shut this down. I'll be back tomorrow night. Tomorrow night's gonna be our big show, our big 2 hour show. I think I'm gonna do whiskey trivia tomorrow night, but I'm not 100% sure. I might take a risk and bring in our new panel software that I'm working with. I've cut ties with StreamYard. I've canceled my membership with StreamYard. I'm done with StreamYard. I don't want to mess with that shit anymore. I believe what I'm going to do now going forward is maybe work with use Skype, and I may try that tomorrow night. Lisa's out of town tomorrow, so I've got our big show. Um, I got a big cough coming. I want to wrap this up before I die. Anyway, it's been fun, guys. This is math is a great. It's a great hobby. I love doing it. I love talking about it. I love showing it. I hope I didn't get too wonky and too deep in the details. Uh, because it was basically a very broad overview. I wasn't getting too deep into the math. I didn't even show the math with the proportion between the coin and the coin and the moon and the distances. It's like 108 to 1 or 180 to 1. I can't remember the number exactly, but like I said, there's scores of YouTube videos. You can go look them up. You can go find this shit. It's not hard to find. If you want data and details and information, it's there. It's available. And you can literally take a pen out and do the math and do the work. It's not that complicated. You may have to remember it, you may have to refresh your memory a little bit, but like this stuff it really is intuitive. Once you learn it, it's intuitive. Um, what time did I start? What time do I start? I start on uh, tomorrow night. I start at 9. Tonight I started at 10. Didn't I start at 10? Yeah. Our short shows start at 10. Our long shows at 9 o'clock. And I'm really seriously thinking about doing live Friday night shows from the distillery. Uh, the weather's still a little bit iffy for Friday night shows, and because we still have to do the shows outside. But I'm working on it. I'm trying to figure out how to do this and do it well. Um, when you hide them, it's blocking them from the chat. Oh, okay. Yeah, that's cool. That's what I want to do. I want to block them from the chat completely. It's fine. I don't care. Uh, I mean, at least if they hang around, I get the views and watch time from them, right? Friday. Speaking of which, Friday morning, I'm continuing my quest for 100,000 views. You see the changes that I've made. We'll talk about the changes that I've made this week, the effects that they've had, the results that they've had, and specifically Friday morning's show. If you catch it, it'll be 11 o'clock in the morning or 10 o'clock in the morning. I can't remember when I have it scheduled. It's either 10 or 11. Specifically, I'll be talking about avoiding bad advice and the good advice that I've gotten and taken, and the 7 really good pieces of advice that I've gotten. And spoiler alert, not really a spoiler, I suppose. There are 7 pieces of advice that I'm implementing, and I am currently on step 4 of the 7. So it's fascinating to see the small changes, and maybe they're big changes, and the effects of those changes and how they've paid off in a very short, immediate time. I can show those to you on Friday. Um, tomorrow on Thursday giveaway show to 9 p.m. Eastern. Yeah, that'd be great. 9 p.m. 9 p.m. Eastern. You finish at 8 p.m. I start at 9 p.m. Central Time. You're done at 8 p.m. Central Time. I start at 9 p.m. Central Time. So yeah, go on, send people over. I appreciate that, Bourbon Bounty. I will. I'll even share out the link to your show tomorrow on my community tab. Make sure to get the two people that look at my community tab to know that something's happening on your shop. And that, by the way, is the reason I'm doing this quest for 100,000 views, to add more visibility to the channel, so that because for the first 2 years of operation, from April to now, basically 2 years, I haven't done anything as far as building community or effectively marketing or effectively messaging the channel out to the YouTube algorithms, and it shows. It really does. It shows on the data and the analytics. I never looked at data and the analytics. I'm just a fucking goofball with a camera. But when I actually started looking at the data and the analytics, I realized literally, like, I joked about it, like nobody's watching the show, but like literally nobody's watching the shows. And I'm trying to correct that. I'm trying to amend that and fix that, so that when I do have guests and live music and people coming on the show, really cool interviews like Tanya, our science advisor, and uh, Slade Ham, a brilliant comedian, voice artists like Rob Mungle and Jenny Strader, uh, other horror movie bloggers like Molly. Uh, I forgot her last name, but we've had really good, really fascinating, really fun guests, and nobody's seen it. But when I have those people on, I want them to be seen, so that uh, there's a whole point, there's a reason to come on the show. Like, you'll actually be seen by at least a couple hundred people. So I'm trying to fix that and get more views. And I assume, I hope, I presume that with more views will come more subscribers. That's like the ultimate down the road metric. But that also means I have to make better shows. And I'm working on that too, because you'll notice we haven't had any freeze frame max headroom moments, because I've played with the settings and kind of fixed how we're streaming things out. Things are much, much better now. The true test is going to be if I do a panel show tomorrow. Uh, Whether or not the panel show survives and doesn't choke out. Um, so there you go. But ladies and gentlemen, go check out Bourbon Bounty tomorrow night at 6:45 Eastern time. That is your Thursday. Is it your Thursday giveaway show? Yes, your Thursday giveaway show. So go check out Bourbon Bounty. The twos and twos of you who are watching now. Uh, and I will post that as well on my community tab tomorrow, so that people will be able to see it. And yeah, send people over. And we'll do, and that's what I'll have the link in chat. If I'm doing the panel show, I have the link in chat. If something else comes up, then I may do something else. But I'll have the link in chat. Uh, we'll do a trivia show. Oh, excuse me. I've been on the verge of coughing for like the last 5 minutes, but I'm not going to play this game anymore. We're going to wrap this up. It's 11:15. I need to go to bed. Ladies and gentlemen, brothers and sisters, children, I shouldn't. Yeah, well, I should though. Got nothing else to say when you stop talking. Ladies and gentlemen, brothers and sisters, children of all ages, thank you so much for visiting and participating with us tonight. I'll be back tomorrow. Tomorrow night, 9 p.m. for our big show. Thursday night, happy hour live. 9 to 11. Is that when the show starts? On Thursdays? Yeah, it's like 9 to 11. Because our short shows are 10 to 11. And we'll also be here Friday for our quest for 100,000 views. So come and join us. Cheers to all of you. Be awesome to each other. And may you live 100 years in a day. And I but 100, so that I never know a day without you. Cheers and good night.